Hello everyone, and welcome to today's lecture on Kalman filter and digital signal processing. My name is Jashwanth, and over the next 15 minutes, we are going to explore one of the most elegant and widely used algorithms in all of engineering. An algorithm so powerful that it helped land humans on the moon. Let's get started. Lectures. So we'll begin by asking why we even need Kalman filter. The motivation, then we'll define what it is and look at it from DSP perspective and understand the mathematical system model it's built on. Next, we walk through its working principle, the famous predict and update cycle, and dig into the Kalman game, which is really the heart of the algorithm. Finally, we'll see its real-world applications and end with a look at how it extends to the unscented Kalman filter for nonlinear problems. And let's jump in. So, before we talk about the solutions, we need to talk about a problem. So imagine you're tracking an aircraft using radar. Your radar sensor gives you a position reading every second, but that reading always has some noise in it. Maybe it's off by 50 meters or 100 meters and whatever. This is the reality of the real world sensors. At the same time, your mathematical model of aircraft motion isn't perfect either. It doesn't account for every gust of wind, every tiny engine thrust variation. So you're stuck. You have a noisy sensor and a noisy model. And you need the best possible estimate of where the aircraft actually is right now in real time. This is exactly the problem of Kalman filter was designed to solve. So it gives us an optimal, recursive, and real-time estimation that minimizes the error in our state estimate. As you can see in the diagram on the right, the dashed red lines is what a sensor might report, and the solid T line is a true signal. The Kalman filter's job is to get as close to that true line as possible. So, the next part. be- So, before doing all that, we have to know what is a Kalman filter. In simple terms, Kalman filter is a recursive optimal state estimator. It uses a mathematical model of the system and incoming sensor measurements to produce the best possible estimate of the system's true state. Let's unpack those keywords. The first one is recursive. The Kalman filter is called recursive because it updates its estimate step by step as new measurements arrive. At every time instant, it uses only the previous estimate and current measurement to compute the new estimate. It does not require storing or reprocessing all past data, which make it memory efficient and computationally fast. This is this recursive nature allows the filter to continuously refine its estimate in systematic manner, making it making it suitable for long-term signal processing applications. And then it's optimal. The Kalman filter is considered optimal because it provides the best possible estimate under certain assumptions. For linear systems with Gaussian noise, it minimizes the mean square estimation error between the true state and estimated state. In other words, it produces an estimate with the minimum uncertainty among all linear estimators. This is optimality is achieved by carefully balancing the predicted value and the measured value by the Kalman gain. So the we have to go for real time now. Kalman filter operates in linear time because it processes each measurement as soon as it becomes available. It updates the estimate immediately without waiting for the future data. This makes it highly suitable for dynamic systems where instant decisions are required, such as navigations, tracking, and communication systems. Since the computational steps are simple and recursive, the filter can run efficiently on embedded systems and real-time processes. And the next one is linear. Its standard form works with linear systems and measurement models. And it was named after Rudolf Kalman, who introduced it in 1960. Its first major applications was navigation for Apollo spacecraft. And next one is about Kalman filter on based on DSP perspective. Now let's position the Kalman filter within the world of digital signal processing. You're probably familiar with classic filters like moving average or weaning average filter. So let's compare them. A moving average filter is a simple and caustic, but it has no model. But it has no noise model. It just averages recent samples and it cannot adapt. And Wiener filter is statistically optimal, but it requires stationarity, meaning the statistics of the signal can't change over time. And it's non-causal, meaning it can't run in real time. The Kalman filter, it's causal, it runs in real time, it can handle non-stationary noise, and it adapts every single time step. So, and I mentioned something called offline and online here. What does that mean? We start with offline process. So offline is nothing but you first record the entire signal, store it in a memory, and then process it later. So the algorithm can see the past data, present data, and the future data. Now, in case of offline, suppose you record ECG for 10 minutes. Then later on your computer, you apply Wiener filter and using the whole signal, you are doing all the necessary calculations to find it. Now, we have to know what is an online signal. This process where data is coming. Data arrives sample by sample. Processing happens immediately. No need to wait for future samples. So the algorithm sees only past data and the current data and no future data. For an example, you can use the same Kalman filter. Suppose you're tracking a car using GPS. Every second, a new position arrives. Kalman filter update instantly. This is online processing. So next we have to talk about the state space system model. So to understand how a Kalman filter works, we first need to understand the state space model it's built on. So there are like two equations. The first one is the process model or state transition equation tells us how the system states evolves over time. Xk is equal to a dot x of k minus 1 plus b dot u of k and plus w of k. So here x is a state vector. For example, like position and velocity of a drone. And A is a matrix that tells us how the state evolves. And B and UK handle any control inputs. And WK is a process noise, the uncertainty in our model. So the next one is nothing but the measurement model. It's basically the observations, whatever the sensor observes. So here ZK is equal to H of XK plus VK. Here ZK is the raw sensor reading. H maps H maps the state to the measurement space. For example, if we can only measure position but not velocity directly, and Vk is a measurement noise. These two equations are the foundation. The Kalman goes in the state space world. Here H is the observation matrix. And the next slide. Now we get to the core algorithm, the famous predict and update cycle. The step one is basically the predict. Using a system model, we project the state forward in time. Xk minus is equal to a of x of k minus 1. Here x of there's something like a minus sign on top. It's basically nothing but the past inputs we're taking. That's all. So this gives us the predicted state, our best guess before seeing the new measurement. We also predict how uncertain we are, like tracked in error covariance matrix P. The P which is nothing but the predicted error covariance matrix. So even that also takes those old inputs and then we are calculating the final predicted error. And the step two is basically the update part. Now the sensor measurement ZK arrives. We compute the Kalman gain, which we explain on the next slide, and then blend our prediction with the measurement. Here xk is equal to xk minus plus k of k into z of k minus h into x of k minus. The term in the parenthesis xzk minus h times xk minus is called the innovation or the residual. It's how surprised we are by the new measurement. If it's small, our prediction was good. If it's large, the measurement is telling us something new. We then update P to reflect our new lower uncertainty. And that's it, repeated for every new time step. The filter is self-correcting and never needs to be restarted. And the next part is nothing but the Kalman gain. The Kalman gain K is the single most important quantity in the entire algorithm. Let me explain it intuitively. The Kalman gain is essentially a ratio, where the formula for Kalman gain is nothing but prediction uncertainty by prediction uncertainty plus measurement uncertainty. So it asks, which source do I trust more? Either my model or my sensor. Three scenarios. If K is near 0, the measurement noise is very high. The filter says I don't trust the sensor reading very much. It mostly follows its own prediction and barely corrects. If K is 7.5, both model and sensor have a similar uncertainty. The filter gives them equal weight and produces a nice average. If K is near 1, the model is very uncertain, but the sensor is reliable. The filter almost completely follows the raw measurement. The beautiful part is the Kalman gain is recalculated every single time step. It automatically adapts based on current noise conditions. You don't set it, the filter figures it out for you. So now I get you an example of like a normal part. Here, this image illustrates about a car tracking system here. The Kalman gain K controls the balance between the system model and the sensor measurement in this Kalman part. It shows three different cases for tracking those car position. Uh, like I'll explain you all the markers here. The blue marker is basically the prediction, and the red cross is represents the noisy GPS measurement, and the star represents the final Kalman estimate. In the first case, where the K is 0, the filter completely trusts the model and ignores the sensor. So the final estimate remains exactly at predicted position. Even though the GPS reading is different, the situation occurs when the sensor is very noisy and unreliable. Now take the second case where the K is zero point 0.5. So here the trust balanced one. See here the prediction is 20 meter and the GPS measurement gave us 36 meter. But the final Kalman estimate what it does is it takes the midpoint of it. So this is what it does for case 2. Now if you take the case 3 where K is equal to 1, the Kalman filter completely trusts the sensor and ignores the model. So the final estimate matches the GPS reading exactly. This happens when the sensor is highly accurate and the model is uncertain. Overall, the image demonstrates that Kalman gain determines how strongly the filter corrects its prediction using the measurement by automatically adjusting this value based on uncertainty. The Kalman filter intelligently combines prediction and sensor data to produce most reliable estimate in real time. And now we want to talk about Kalman filter recursion flow, which visualize the complete cycle one more time. We start by initializing it, giving the filter an initial state estimate and an initial uncertainty. And then we go to the predict state. Use a simple system model to forecast the next state and finding the state and covariance matrix for the calculations. Then we update. Incorporate the new sensor measurement using the Kalman gain. The output is our best estimate x of k. And we can just repeat this entire process again and again with different k values. And then we already discussed what is innovation residual part. It's basically the difference between what we measured and what we predicted. The Kalman gain decides how much of this difference we should trust. Then we have to talk about slide 10, intuitive analogy. Let me give you a real world analogy that ties everything together. Imagine you're driving through a tunnel and you use GPS signal. Your GPS signal is weak, and what do you do now? You use something called dead reckoning. You know your speed, you know how much time has passed, so you estimate your position, and that's the predict step now. When you exit the tunnel and GPS returns, you check your actual position and correct your estimate. That's the update part. Now, and here is a critical question: how much you trust the GPS reading versus your dead reckoning? If the GPS signal is weak and jumpy, maybe you weight your own calculation more. If the GPS is strong, you trust it fully. The trade-off is exactly the Kalman gain. The Kalman gain does this automatically, optimally, and continuously for any linear systems. Now we have to talk about the applications around across industries. The Kalman filter isn't just theoretical; it's everywhere. Navigation and GPS, radar tracking, robotics, IMU sensor fusion, financial models, and brain computer service. We talk about it one by one. For navigation and GPS, it powers every commercial aircraft inertial navigation system and was used in Apollo spacecraft. And radar tracking. Aircraft air traffic control systems track hundreds of aircraft simultaneously using Kalman filters. And even military uses this for target tracking and missile guidance systems. Then robotics. Self-driving car use it for SRAM, building a map while tracking their own position. Then is the IMU sensor fusion. Your smartphone screen rotation is driven by Kalman filtered combination of accelerometer and gyroscope data. And finance models used to estimate hidden volatility in stock markets and filter noisy time series data. And even used in neuroscience also, basically in brain computer interface. EEG, brain signal denoising, and prosthetic limb control rely on Kalman based filtering. Truly one of the most impactful algorithms ever invented. Now we have to talk about some of the limitations it causes. Now, no algorithm is perfect. The standard Kalman filter has some important limitations. It assumes linearity. Both the process model and the measurement model must be linear equations. Many real systems like a spinning satellite or a swinging pendulum are nonlinear. It assumes Gaussian noise. If your noise follows a different distribution, performance degrades. It requires known model parameters. If you have A, H, Q or R matrices are wrong, the filter can actually diverge and produce worse estimates than doing nothing. These limitations motivated researchers to develop extensions, most notably the extended Kalman filter and the unscented Kalman filter. And we have to compare it now. The standard Kalman filter introduced in 1960 is exact optimal solution, but only for linear systems. It has good amount of strength and its method is for closed form equations and no approximations. But it can't do nonlinear models. But if you talk about extended Kalman filter, handles mildly nonlinear systems by linearizing them. It computes the Jacobian matrix at each step to approximate the nonlinear function locally. It works well for slightly curved problems, but breakdowns for highly nonlinear systems. And finally, the unscented Kalman filter, developed in 1997 by Julia and Ullman, takes a smarter approach. Instead of linearizing it, it picks a set of carefully chosen points called sigma points and passes them through an actual nonlinear function. The result is propagated to estimate the mean and covariance of the output. It's significantly more accurate for highly nonlinear systems with only an increase in computation. If you go on to study advanced estimate theory, UKF is usually the next topic after mastering the standard KF. And summary and takeaways. Let's wrap our lecture with a summary. The Kalman filter is an optimal recursive state estimator that gives the best possible estimate from noisy measurements. Its predicts update cycle is elegant and computationally efficient, making it ideal for real-time DSP applications. The Kalman gain is algorithm's intelligence. It automatically balances trust between the model and the sensor. It has widespread applications across like navigation, robotics, signal processing, finance, and biomedical engineering. And it forms the foundation for more advanced nonlinear filters like EKF and UKF. I hope this gives you a solid intuition for how the Kalman filter works and why it matters. Thanks for watching and feel free to reach out with any questions.